Gauss's law is one of the fundamental equations of electromagnetism. To make sense of it, consider the electric field of a point charge Q sitting at rest. Its electric field lines are reminiscent of the jets of water that you might see spraying out from a sprinkler. In fact, pushing that analogy a little further, if we wanted to measure the strength of the sprinkler, we could imagine surrounding the whole thing in a giant rubber balloon and measuring how much water per unit time is hitting the surface. In a similar way, let's picture an imaginary sphere surrounding our point charge. Then the strength of the field lines passing through the surface should give us a measure of the amount of charge contained inside. To make that idea precise, imagine slicing the surface up into lots of tiny patches. For each patch, we can construct a vector dA, whose magnitude is the area of the patch and whose direction points perpendicularly away from the surface. By taking the dot product between that area vector and the electric field vector at the location of the patch, we get a number that quantifies the strength of the electric field that's passing outward through that tiny area. Next, we'll add up the contributions from all the little patches making up the sphere by integrating the dot product over the entire surface. The result is a number called the electric flux passing through the surface, and it would correspond to the amount of water flowing outward per unit time back in the sprinkler analogy. Here in the electric case, the flux is supposed to measure for us the amount of charge contained within the surface. So let's see what we get when we plug in Coulomb's formula for the particle's electric field. We can begin by pulling the constant factors out front, including the constant radius r of the sphere. As for this dot product, remember that the area vector is defined to point perpendicularly away from the surface, which for a sphere just means that it points radially outward along the r hat direction. And when we take the dot product of the unit vector r hat with itself here, we just get 1. Then what we're left with is the area dA of each little patch, summed up over all the little patches making up the entire surface. And that sum is simply the total area of the sphere, 4 pi r squared. So lo and behold, the factors of 4 pi r squared cancel, and therefore, just as we'd hoped, the total electric flux passing through our surface has indeed told us the amount of charge Q contained inside of it. And this is in fact a completely general property of the electric field that holds for any configuration of charges and for any surface S surrounding them. It doesn't necessarily have to be a sphere. And it's known as